In this video, we will be talking about the work energy theorem. So in the previous videos about work and kinetic energy, where I individually covered both of them, I kind of foreshadowed the work energy theorem. And the work energy theorem is just like so. So the work you apply to something is equal to the change in kinetic energy. And you can also represent your change in kinetic energy as your final kinetic energy minus your initial. Let's write initial kinetic energy. So this is the final. This is KEF. Actually, I can just write K. This is K of F. And this is K of I. So this is the initial kinetic energy. So final minus initial equals change in kinetic energy, which makes sense in this case. So this is a core theorem that you need to know. And let's just cover a few things that you need to know about this before you move on to some of the problems. So let's say you have a box. It's got a velocity of 1 meters per second. Very easy to calculate. And it has a mass of 5 kilos. So the kinetic energy for this is equal to 2.5 joules. So if you apply some work on this box, then let's say you apply a joule of work, well, that means your kinetic energy is now 3.5 joules. And using this, you can solve for the kinetic, you can solve for the speed. And if you apply a work of negative 1 joule, well, now your new kinetic energy is 1.5 joules. And again, using your kinetic energy formula by reversing everything like so, v squared, you can solve for your velocity by just isolating it. Now that you know that, now that you know a negative work changes your kinetic energy negatively, and a positive work changes your kinetic energy positively, let's go into some problems. So for this problem, you need to calculate a force needed to bring a 950 kilo car to rest from a speed of 90 kilometers an hour. So let's do some unit conversion first. So doing this unit conversion, the kilometers cancels out and the hours cancel out. So we get left off with meters and seconds as our unit, and the answer for this is 25 meters per second for our initial speed. So this is VO or VI. Okay, so now that we have that in the right unit, we also have the distance traveled. So R, when calculating work, is equal to 120 meters. And the work energy theorem states that work is the change in kinetic energy. So suppose calculate the force needed to bring a 950 kilogram. I just skipped parts. Oh my goodness. Okay, calculate the force needed to bring a 950 kilo car. So what does this indicate? Well, we want to calculate the force, and force is related to work. So we have the distance, but our force is unknown. But we know that force is change in kinetic energy. And if you want to bring a car to rest, we want the kinetic energy to equal 0 joules. So we need to find the current kinetic energy of our car, like so. And this all equals 2.97 times 10 to the power 5 joules. So that's a lot of energy in this car. And what we need to do next is we need to find the work. So what is our work here? Well, if we want the kinetic energy to be 0, which means the car's at rest, so we want to bring the car to rest, we want the change in kinetic energy to be equal to the negative of the current kinetic energy. So we want our change in kinetic energy to cancel all this out so it turns into 0. So cancel all the kinetic energy of the car out so that it turns to 0. So we want our work to be, well, the negative of itself, the negative of the current kinetic energy, so that all this cancels out. And to set up this equation, you need to write down this as the equation. And the reason why I didn't include the cosine is because both the force and the displacement should be equaling or going in the exact opposite direction. Since you're trying to stop the car, the force is going in the opposite direction. So your displacement will be 120 and your force will be some positive magnitude. And multiply by -1 because of the cosine of 180. As that is the angle, 180 is the angle between the force and the displacement vector. So once you solve for force, you just get approximately 2475 newtons. So this is for part A, and this is the force required to bring the car to a stop within 120 meters. Now, how about this? Suppose instead the car hits a concrete abutment at full speed and is brought to a stop at 2 meters. So that's a lot shorter distance. So we're going to expect the force to be a lot greater in order to stop the car a lot, or decelerate the car a lot quicker. So maybe we could just write that here. So we want to stop the car in 2 meters this time. So R is 2 meters. But our kinetic energy of the car is still the same. We still use the same kinetic energy, so let's keep that in mind. And we still need the same work in order to bring the car to the stop. So again, we just need to set up an equation like so, where this is the equation for work. So our work needs to be negative of the kinetic energy in order for the change in kinetic energy to be 0. In order for the kinetic energy to be 0, sorry. And we're just setting up our dot product formula. The magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And since the force of stopping a car goes in the opposite direction, you would assume that opposite direction of displacement, you would assume that cosine of 180 would be here. So all you need to do is just solve for the force for part B, and you would get an absolutely ridiculous force of, I think this is 149,000, yeah. This is 149,000 newtons. So, it says compare it with the force found in part A. So I'm just going to explain it real quick. Well, it's obviously significantly greater than 2,475 newtons, right? And the reason why is because in order to stop a car within a shorter distance, you just need to apply a significantly greater force in order for you to do the same amount of work in a shorter period of time. And if you look at all the formulas, it'll make sense. So let's do the next problem. Boxing gloves are padded to lessen the force of a blow. Calculate the force exerted by a boxing glove on an opponent's face if the glove and the face compresses at, so 7.5 centimeters. So 7.5 centimeters is also equal to 0.075 meters. During a blow in which the 7 kilo arm, so that's the mass, and glove are brought to rest from an initial speed of 10 meters per second. So let's find the kinetic energy. So this is the kinetic energy, the initial kinetic energy of the arm. And once you solve for initial kinetic energy, the initial kinetic energy is equal to 350 joules. So we want to find the force exerted by a boxing glove. Well, we know that per the work energy theorem, work is equal to the change in kinetic energy, and we want to know how much force it takes to, well, completely stop the arm. So, in order to completely stop the arm, the final kinetic energy must equal 0 joules. So our work must equal the negative of our kinetic energy. So work must equal the negative of our current kinetic energy, so that the change in kinetic energy, or the work, will turn the initial kinetic energy to 0, which is exactly what we want. So once we solve for the work, we can write down the formula for work, where the formula for work looks like so. The magnitude of the force times the magnitude of the displacement times the angle between them, and the force exerted by the face onto the boxer's hand that's stopping the fist is going in the opposite direction of where the fist is displacing into. So the angle between them is 180, which makes sense since you want the work to be negative. Now, once you solve for force, your force will be approximately be equal to 4,667. The exact answer is just 4,666.6 repeated. So this is your force that you're releasing onto someone's face if you punch them with the boxing glove. But how about for part B? So this is for part A. How about for part B? Well, for part B, now you're doing bare knuckle. So, ooh, yikes, that's going to hurt a lot more for someone because you're actually doing work within a shorter distance. Therefore, you're exerting more force onto someone. So, calculate the force exerted by an identical blow in the days when no gloves were used. I don't get why OpenStax mentioned in the days where no gloves were used. What? Okay, and the knuckles in the face would compress only 2 centimeters. So identical blow. Assume the change in mass by removing the glove is negligible. So your initial kinetic energy will be the same. So K of I is still equal to 350 joules. Therefore, our work is still equal to negative 350 joules since we want to bring the final kinetic energy to 0 joules. And we the only thing that changed is your displacement. So R is equal to 0.02 meters now, as that's equal to 2 centimeters. So let's set up our work equation. So this is our work equation, just a simple dot product, magnitude of force, magnitude displacement, and the angle between the force and the displacement. As I've already explained, the cosine of 180 signifies that the force and the displacement go in exactly opposite directions. So once you just do a little bit of algebra here and isolate force, you get a force of 17,500 newtons. Ridiculous amount of force, and it's significantly greater than the boxing glove. That's probably why it hurts a lot more to get hit by something harder, especially since, for brass knuckles, that metal doesn't bend at all. It probably bends like, I don't know, like a micrometer when it hits your face. So that's probably why it hurts so much with those. But yeah, not at this point. I'm just yapping. Okay, let's go to the next problem. So this problem, a lot less details, a lot more parts. So let's go through all of this. So a 5 kilo box has an acceleration of 2.0 meters per second squared. So this is already an indication of net force. Net force is equal to mass times acceleration. We can solve for the net force by multiplying 5 kilos by your acceleration to get 10 newtons. So 10 newtons so far is our net force. When it's pulled by a horizontal force across a surface with a kinetic friction of 0.5. Therefore, this object's moving, so there's kinetic friction coefficient. Find the work done over a distance of 10 centimeters. So let's write that down. 10 centimeters. 10 centimeters is equal to 0.1 meters. Find the work done over a distance 10 centimeters by the horizontal force. So part A, part B connect together, but we need to find the friction force first. I feel like that's the important thing here, because there's no way to solve for the horizontal force without solving for the friction force. Let's solve for the friction force first. The parts of this are written pretty bad, but the friction force is just normal force. So normal force, this is just weight, where 49 newtons is your normal force and also your weight since you're on a flat surface. And you just need to multiply your normal force by your coefficient of kinetic friction to get the frictional force. So this is 24.5 newtons as our friction force. So if we were to draw a quick free body diagram with the weight, let's just draw the weight and the normal force real quick. We will have our push force, which is unknown, F push, what we're trying to solve for in part A, and our frictional force. So friction of kinetic friction. But since we know the mass and the acceleration of this box, we know the net force is 10 newtons. And since your push force is greater than your frictional force in this case, then you just need to add 10 newtons onto your frictional force to get your net force here. So 34.5 newtons is your horizontal force. Now, the net force, we can already calculate that. The parts for this are written pretty bad, but the net force we already calculated. It is 5 times 2, which is 10 newtons. This is Newton's second law of motion. And what is the change in kinetic energy of the box? Well, the change in the kinetic energy of the box is the work, correct? So work is equal to change in kinetic energy. I guess I'll write part C here, specify it. And let's write part D here. If our change in kinetic energy is the work of the box, we just need to write down the formula for work. And the formula for work is net force times the displacement times the angle between the force and the displacement. And we know that the force of the push goes in the same direction as the displacement, so the cosine of 0 makes sense, as that is the angle. 0 is the angle between the vectors, between the force and the displacement vector. So once you multiply this together, you get a work of 0 joules. And since the work is 0 joules, our change in kinetic energy is also 0 joules. So this solves for part D. Okay, how about for part E? What is the speed of the box? Well, in order to solve for the speed of the box, we need to set up our kinetic energy formula. And our kinetic energy formula is written like so: 1/2 times 1/2 times the mass times the velocity squared. But we don't know this, well, speed squared technically, but we don't know the speed, well, we know the kinetic energy. So if you just do a little bit of algebra, isolate your speed variable, you get approximately 0.632 meters per second for your speed. Now, you can use kinematics to solve this. You have an acceleration, you have a distance traveled, and you start at rest. So you can use kinematics to solve this, and you can actually check if this is right. So, as always, need to mention OpenStax, free online textbook. Link will be in the description if you want to check it out. I get my problems from there. And also another thing, I will have some links in the description for work and kinetic energy. So if you don't understand both of these individually, then the work energy theorem will be pretty hard. So I have videos on this also. Links will also be in the description. But as always, if you have any questions, leave them down in the comment section.